Thank you all. So my name's Joanna. I'm a PhD student at MIT and affiliated with a group called Seismics, where we contribute to developing an end-to-end Julia workflow for molecular simulation. And today I'll be talking about a package that I'm developing called Cairn, which is a library of algorithms for enhanced molecular dynamics for active learning. So earlier this week, Rachel Kirchen and Michael Herbst gave an excellent keynote, which motivates why we care about multi-scale modeling and computational material science, where numerical simulation models can help accelerate the process of materials characterization and discovery. Even with advancements in high-performance computing, simulations at the quantum scale using DFT remains cost prohibitive for systems larger than a few hundred atoms. And for that reason, we're interested in developing machine learning interatomic potentials, which serve as surrogate models at the atomistic scale, which are trained on quantum calculations and achieve the same accuracy at a fraction of the cost. Now, the challenge here is the same as with any machine learning model, which is that the model is only as good as the data that you train on. So we operate in the regime of small data sets, meaning that our models can be subject to high uncertainty. And in molecular applications, the landscape of configurations that we train to is often highly multimodal and high dimensional. So we can understand this using an illustrative example. Consider that we have a carbon monoxide molecule, which has a double well energy landscape. Each well corresponds to an equilibrium state of the molecule with a different bond length. We sample configurations along this landscape by a process called molecular dynamics, or MD simulation, where we simulate Newton's equations of motion for the atoms. Now, carbon monoxide has a strong bond, meaning that it takes a large amount of energy to pull the atoms apart and change its bond structure, which corresponds to a tall barrier between the energy wells. And since the force acting on the atoms is related to the gradient of this potential energy landscape, then we see that the trajectory remains confined to this local minima, and we never observe the molecule in its second equilibrium state. This is a major problem when we use MD trajectories to generate training data for machine learning models, because models trained on an insufficient subset of the state space can lead to unreliable predictions. So for this reason, we're concerned with this question of how do we drive MD simulations to explore new regions of the state space? So this is one component of the larger objective of active learning for scientific machine learning models. The goal here is that rather than take the naive approach of simulating a bunch of data for your training set, which can be very expensive and inefficient to label, we want to be more intelligent with our selection and query new data which maximally improves the accuracy of our model. So our team at Seismics has a Julia package for each step of the active learning loop. The first step is to generate data by sampling. This can be done using enhanced samplers in the package Cairn, which is built as an extension to ML-I, developed by Joe Greener. This package interfaces with interatomic potentials for defining the form of our machine learning model with trainable parameters. The second step is to generate trajectories and then select an optimal subset of that data to then label and append to our training set. So Cairn also includes methods for data subset selection methods, and labeling can be done using reference calculations, such as with DFTK, developed by Michael Herbst. The third step is to train the model on the augmented dataset. So potential learning is our package containing functions defining objectives for learning the parameters of the machine learning model from data. And finally, the fourth step is to evaluate the accuracy, stability, and performance of our updated model for characterizing various material properties. So atomistic QIs is our package now for calculating these quantities of interest using the updated model. And the idea here is to apply these steps in an iterative loop, which is terminated after we've reached some threshold of model accuracy. Here, the colored package names are in-house packages developed by Seismics, which importantly interface with tools that are developed by our collaborators at JuliaCon. And today's talk focuses on Cairn, which is the master package that ties together the others as dependencies. So this package is structured to maximize composability. In our active learning loop, with each time step, we have a simulate function defining the equation of motion used to advance the trajectory and sample our next configuration. We evaluate whether a trigger has been activated for stopping the simulation and updating the model. If it is activated, then we define a scheme for selecting a subset of the data to label and append to the training set. And finally, we retrain the potential on the augmented set using an objective defined in the learn function. So the idea here is that users can flexibly exchange methods that are specified under each of these abstract types. Among simulators, we can run standard samplers for MD simulation or enhanced samplers, which encourage diversity and exploration. Among triggers, we can have a fixed trigger over a fixed number of time steps, or adaptive triggers based on some criteria related to uncertainty, extrapolation, or diversity metrics. Among subset selectors, we can make a basic selection, such as a random subset of the trajectory, or we can make an adaptive selection using an algorithm such as d-optimality, DPPs, or CUR. And then finally, among learning problems, we generally train using least squares loss and energies, forces, or both. One could also frame this into a Bayesian inference problem through the definition of a likelihood and prior over the parameters. Okay, so I'll show a few examples of how Cairn can be used to implement various active learning algorithms in literature. So for example, one could implement FLARE by choosing velocity relay as the simulator. Model updating is triggered when the trajectory reaches a region of high uncertainty as measured by a Gaussian process. We choose a subset of data with the largest uncertainty estimates for retraining the model using a standard objective function. Uncertainty-driven dynamics, or UDD, can be implemented as a custom simulator where we introduce an additional biasing force that drives the trajectory toward regions of high uncertainty as measured by the variance of predictions from an ensemble of models. So these could be the same neural network model with different initialization of the weights. And then similarly, we choose data associated with high uncertainty for appending to the training set and updating our model. Finally, Cairn is home to a novel active learning algorithm that we're currently developing called Stein Variational Molecular Dynamics, or SVMD. And it works by introducing repulsive biasing forces that drive the trajectory away from the existing training set to encourage diversity in the resulting dynamics. So here's a quick demo of the method, where to the left we see contours of a 2D machine learning potential trained on an initial set of data in red, and the trajectory is shown in green. Here, the initial training data is concentrated in one well of the potential, and the goal is to see how efficiently our simulator can sample from the other well.
Okay, sorry to interrupt you here, but we're out of time.
Okay, yeah, so I'll just run through the rest of this to show you that with our custom simulator, we're able to more efficiently sample from the state space and have the contours of our machine learning potential recover the true contours. And here are a few kind of summarizing points. With this, I'll wrap up my talk, and thanks for your attention.